Hi all, we'll just wait a couple minutes for all the tired East Coast people. Hi all. Hi all, we'll just wait a couple minutes for all the tired East Coast people. Okay. We'll get started then. Hello, everyone. Hello to my colleagues as well. We're like mainly not in the office because LA is being LA right now in a bad way. Sometimes it's LA in a good way, but right now not so much. So I hope everyone's doing well. Happy New Year. I'm Natalie. I'm the lead for IAP this month. And I'm really excited to talk to you guys. I feel like I haven't just like talked to a computer in a really long time, so if I seem tired, just like yell at me. It'll help. If anyone has questions, if Gridspacers could monitor the chat and then like just shout them out because I'll have a hard time doing both. If there's any questions now, I'm gonna close this little Google Meet thing because it's bothering me. Okay. Cool. So today we're gonna talk about acoustics and signals, mainly signals. That's my background. So just a couple of announcements. Tomorrow's lecture will be canceled, like because of the aforementioned bad parts of LA. Where we're supposed to have noise engineering, but they have a power outage, and so they're not able to prepare as well as they want to. So we should be able to get them in on Monday and bump Monday's lecture to Tuesday. So sorry about that. And I'll send that up also in a follow-up email. So today we're headed to the physics of sound and signals, and then the rest of the month will be focused on methods of manipulating these signals, speech synthesis, neural generative models, and we'll have a ton of special guests, as Anthony mentioned. So I hope you're all excited. I hope you're just staying engaged. Please reach out if you think of any other ways that we can support you or make the course more interesting. We're always into suggestions. Cool. So again, revisiting objectives. We're celebrating 100 years of sound technology from mechanical and analog systems up through deep learning. So we'll be focusing on the former today. So we're not assuming any knowledge. So if something is confusing, please ask about it. And I think we'll have to say come to 11 lectures for a shirt because we're not even in for this one today. So you lucked out there. Cool. Audience prereqs. If you don't submit to this, you should leave. Just kidding. You should stay and then make sure you can submit to this at the end. So we hope you're excited about machine learning and sound, know a little bit about programming, and then some mathematical knowledge, and have ears, hopefully. Okay, cool. Here's the course schedule. It's also on our website, iap.gridspace.com. I'm your course lead, Natalie Bechet. I'm also Natalie at gridspace.com if you want to just email there instead of the IAP. So our videos will be released after the live streams. And we'll be sending you meeting invites, all of you. I'll ask about a copy for the slides. I'm not sure if we can do that at the moment, but good question. And feel free to follow up with me by email if I don't get back to you. Like I did today, I'll send out the meeting invites. You all should be added to the Google group by now. If you haven't been, please reach out to me. If you're in person, like Anthony showed, you should have a little attendance card. And if you're remote, we really want you to be engaged. We're all remote today, so we should have equal amounts of engagement. So please stay with me. Awesome. All right, let's get into it. Can anyone tell me what sound is? I didn't really know before starting this. Anyone? You can message, you can talk. Sound is waves. Okay, that's definitely a box we put sound in, but it's a very useful one, as we'll see through this entire lecture. Anyone else? Pressure, definitely. Pressure is we'll see how those two things come together. Pressure over time, awesome. Yeah, so these are all good and accurate definitions. And they're all going to come into play today. So sound, as we like to think of it, is represents because of a cyclical pattern of particles bumping into each other in physics. So let's watch a little video. Let me know if the sound is good, Kevin or others. Okay. So this is just a brief of the sound wave of a popping balloon.
This graph shows the pressure waves, or waveform, produced by popping a balloon. The vertical axis is pressure, or the amount of force the particles bounce into one another. The horizontal axis is time. These high points in the waveform are called compressions, and they are where the particles are compressed and bouncing around a lot and thus have a higher pressure. The low points in the waveform are called rarefactions, and they are where the air particles are more spread out and not bouncing around as much, and thus have a lower pressure. Both the graph and particle animation help to visualize sound, which, as we know, is invisible to our eyes. The measurements are taken at a single point in space. In this case, the pressure was measured by a microphone. In order for your speakers to duplicate this sound, the diaphragm in your speakers just have to move in a similar fashion. The entire sound takes 1/10 of a second for your speakers to duplicate. This visualization is just the first section of the overall pattern of cycling compressions and rarefactions produced from a popping balloon. In just this quick sound, there were about 50 of these cycles. If we slow down this sound to 4 seconds, you can hear some of the cycles between compression and rarefaction. Most sounds last much longer than this quick duration, so in visualizations of sounds, we usually see the squished version of this graph, which looks like this.
Cool. So Riley on YouTube, hi Riley, said patterns of rarefactions and compressions in a medium. Yeah, that's right. So what's happening as sound is produced and why we call it a wave is because of the cyclical motion of the waves, of the particles hitting each other and then coming back into the space, like rushing back into the space they left, and so on and so forth. And so this is the wave equation. You might be familiar with it. I will not derive it in this lecture, but it's kind of cool, and if you're interested, reach out to me. I just thought it would take a lot of time, but please reach out to me. I have it, so you can see it there. But it's derived from Newton's third law, which I thought was really cool. And this is the basis for how we understand and interpret sound. So the reason why we consider sound as waves and why we can do all of the like manipulations we're going to talk about in this course is because of this equation right here, which is quite fascinating. So I think Uche mentioned that Uche and Phoebe said it was pressure over time. So this is pretty much saying the displacement of the wave with respect to time is linearly equal to, or the acceleration of the displacement with respect to time is linearly equal to the displacement with respect to space. Which again, I have a lot of resources on. I just wanted to focus a little more on signals in this lecture, but you feel free to reach out to me if you're interested in that derivation. So yeah, waves are key, and they're going to guide the rest of our discussion today. So this is the speed of sound, 43 meters per second. Very English of me. So what is acoustics? Acoustics is the science of physical and mechanical waves. So in this lecture, we're going to talk about the mechanical manipulation of waves, and then the electronic manipulation of them and the electronic understanding of them in the signals portion. And so I think that's kind of an important duality to have in mind, is that acoustics and like the study of mechanical waves existed long before signal processing and all of the manipulations we did of waves electronically. But we now can replicate these sounds. We have a better understanding of them because of the developments in electronics and digital signal processing. So let's talk about some acoustic examples. So this is the Helmholtz oscillator. You might have done it if you had a water bottle and you blew over it. So this is just one model that shows how mechanical vibration becomes sound. It just requires a cavity and then a space that's larger than it below it. And this resembles a mass in a spring. And the vibration that occurs will become sound here, as you guys have probably seen. This is another type of mechanical vibrate oscillation in a string, which I think is really cool. So we can play this to see which strings are higher, which strings are lower frequency. He does, I recommend. So you'll notice that like the guitars that are, the guitar strings that are thicker will vibrate with like bigger waves, and the ones that are smaller will vibrate with smaller ones. And they, as we'll talk about a little bit later, they all have what we call harmonics, right? Which is you're not just hearing one frequency, you're hearing multiples of a bass frequency. Sorry. So this is a pretty fundamental concept in acoustics, is that in, basically all instruments, and when Anthony was doing his demonstration on one of the ways we made the instruments sound more real was to add the harmonics. Well, these are the harmonics, right? They're integer multiples of the bass frequency, and all different instruments have a sort of harmonic pattern that they follow. So different instruments, like obviously a guitar, and that's namely not only just because one is a wind instrument and one is a string, but also because of the harmonics that they produce. So these are different modes of a drum head, which also relates to harmonics. Another important topic in acoustics is resonance. Does anyone know what resonance is? Can define it? Have heard of it? That's okay, I can define it. So each resonance vibrates at its natural frequency. So if you guys, the classic example of this is, I don't know if you've seen that video of the bridge that collapsed. So Anthony said one vibrating system coupling with another. Yeah, that's right. So there's a bridge that collapsed. I don't remember when it was, but it's like example. Thanks, Anthony. Tacoma Narrows Bridge, if you want to look it up. Classic example of an engineering failure where the bridge was oscillating at its natural. It was the wind was blowing at the same resonant frequency of the material that the of, and then the bridge essentially got excited and like kind of wiggled up and down in this wave-like fashion until it broke, until the force on it was too strong. So resonance is pretty fundamental. Cool. It's pretty fundamental, obviously, so we can prevent sounds like that, things like that, but also in acoustics. So an example is like blowing across the top of an empty bottle, like we saw, the vibration of a guitar string causing the body of the guitar to vibrate. The wine glass shattering is when one is exposed to a sound at its resonant frequency. Or when a piano string vibrates, when another piano string is vibrating at its resonant frequency. Another example is like a tuning fork. And we'll get resonance. No. This is sympathetic listening. Right, I'll stop it here. Does anyone know, can anyone predict what's gonna happen? Don't be shy. Yeah, they always the vibes will be good too. They're always good here. Yeah, I'll see up to that part. We're getting closer. Kind of cool, right? And that's strictly because of the mechanical systems around it. Actually, they're going to stay upright and they're going to continue vibrating in this way because they all, because of the mechanical system they're in. This was another example with a tuning fork that I like. I think this demonstration looks like really old, but I found it cool.
Tuning forks are wonderful tools for teaching physics. One of the most famous demonstrations is that of resonance. I have these two tuning forks which are on the same frequency, 256. If I sound one of them, the sound gets transported to the other through resonance, and back again. Here's a way you can enhance the demonstration. I've hung a pink...
I don't teach physics, so I will not enhance the demonstration. But you can see, like, since those tuning forks resonate at the thanks, Riley. Yeah, they will eventually synchronize. Since the tuning forks are at the same frequency, they're tuned to the same frequency, they're going to vibrate when they hear, when they feel that mechanical frequency. So it's two things that are mechanically matching. The frequencies are mechanically matching. Another fundamental concept is reverb. I'm sure you've all heard of reverb, reverberation. This is a little meme that my husband showed me when he saw that I was giving this presentation. So this is obviously a joke, but this is real reverb, what you experience. And a lot of the times musicians like will plan for this sort of thing. Thank you, Cooper. I'll give him the feedback. So a lot of the times, like, and we'll probably see later this month, like reverb is a phenomenon that is planned for and can enhance the musical experience, as well as resonance. So we can, it's the persistence of sound after it's produced, and it's because of reflections, right? So it's a reflection that's not, you know, exactly 180. When a sound is exactly mirrored in the opposite direction, but because it doesn't bounce, because the sound doesn't bounce off off of a flat surface, as a call, for example, it'll create this echoey effect with this delay. So you know, we've all experienced reverb before, clapping your hands in a large empty room, hearing a prolonged echo after a choir sings, lingering sound of a guitar after plucking, or speaking in a large hallway where your voice seems to bounce off the walls repeatedly, right? We've all experienced reverb in some sort of way. I have another video. I wish I was a musician. I could demonstrate all of these myself, but you'll have to stay tuned for noise engineering for that. So let's see, you know, some examples of there's some reverb. Reverb, not the nicest note. So she played a resonant tune at the, she found the resonant sound of the room, right? And played that tune, and it seemed to get louder and louder. That's a fundamental aspect of resonance. Like, it will continue, the vibration will continue to increase. It won't just be absorbed. And then an aspect of reverb that we mentioned was reflection. So this is kind of a fun little video. So that goes on for quite a while. I thought it was pretty cool example of reflection where he has it. I mean, I don't know if he built this long, big thing for this demonstration, but he figured out the tempo and the rate that the reflection has to happen for that, for him to be able to play a song like that. So it's cool. Another thing that has to be considered in acoustics is the Doppler effect. Of course, we've all seen this. If, you know, when a car drives by and the horn, you know, will sound differently when it was coming towards you versus when it was going away from you. And that's because the speed at which the wave is hitting you when it's driving towards you is faster. The frequency is higher than when it's going away from you, right? Then the frequency is lower. So as it's coming closer to frequency, put a connection there. So yeah, all of these methods, all of these phenomenon are in acoustics and are used by musicians and anyone who manipulates waves to create really cool effects. Cool. And again, all of this comes from understanding sounds as a wave, and we'll see a lot of examples of this throughout the series. All right, I'm going to jump into signals. Any questions? Awesome. Okay. So digital signal processing. We're going to talk about this from a very fundamental point. So if you're not familiar with this material, no worries. This is mainly to provide exposure and to demonstrate that, you know, we have a physical understanding of waves, and that's extremely important. But the way we manipulate these, the way we're even able to listen, the way we can speak on the phone is all because of DSP. So physics absolutely provided the fundamental understanding and even the reasons why we need to consider sound as a wave. But DSP is how we're able to captivate on that understanding and to expand it even further. So a signal is information over channel, right? A signal is a function that conveys information about a phenomenon, right? So this is an example of a signal. This is also an example of a signal, one that might hit a little close to home. These slides were made before the fires. Smoke is signaling a fire, right? That something is happening. Sorry, everyone. I'm sorry. Moving on. This is also a signal, whereas maybe you guys are doing this right now because of the last one. This is also an example of a signal, right? Like these are all simple in 2D that can be analyzed using signal processing, using 2D signal processing. So as I'm talking right now, or if I was talking to you and we were in the same room, my voice would be the signal and your ear would be, the receiver. And as I'm talking over the phone, or maybe this is like a little different because of Wi-Fi, right? We have a signal and it goes through a lot of things and it's reconstructed into, something close enough to the same signal, right? So signal processing refers to the science of analyzing time varying. So that can be anything. There are multiple time varying physical processes. So signal processing is broken down into two obviously really closely related categories: analog signal processing and digital signal processing. So this is an example of analog signal processing. So you see all these like capacitors, resistors, I can't even believe I remember what those are called, op amps, grounding, power, all the sorts of things that are, hooked together to, analyze a given signal that's coming in through here. This is analog signal processing. So this is how, radio used to work, for example. And this is a guitar amp, which is a lot of circuitry, right? And so what the fundamental mode of signal processing in analog in ASP is circuits, right? So the signal becomes data points instead of just a wave of sound, and then we can do digital signal processing on it. So we have this whole giant schematic, and instead of doing this and using this as a filter, we have some sort of mathematical description for our filter at a point J multiplied by samples at a particular point. And that's an example of convolution, which we'll get into a bit later. So one might look more simple. In reality, there are a lot of the same principles that are applied in both fields, but in digital signal processing, a lot of speed ups because of linear algebra occur, and we'll just allude to them briefly in this presentation. So now, a lot of the times, obviously, as I'm still speaking, right, and as signals are being created in the world, they're still continuous. DSP didn't just, start making things discrete, even though maybe if you're a physicist, you think everything is discrete. I won't get into that. But in my perspective, sound is continuous. Waves are continuous. They are modeled continuously in physics for the most part. And so we have to digitize them ourselves, so we can analyze them. So here's just a quick example. There's an unfiltered analog signal that comes in, and say it's my voice and it sounds really awful, so we want to do some processing to it. So this is seems like a good representation of this wave, and we'll see how we come up with the frequency of that representation soon. And then this is filtered in some cool special way. Maybe I just took my pen or my mouse and I blurred out the edges. Maybe I did something fancier. And then we reconstruct the analog signal, because we don't just want to hear digital signal, hear a continuous stream. This is very fundamental in all of speech synthesis, all of music production, right? This idea that we take something continuous, we digitize it, we filter it, we do work on it, and then we make it continuous again. That's really fundamental process in signal processing. Cool. So the basis and the most important and kind of elementary tool and wave we have is the sine wave. Just a shifted cosine. If you like cosine, don't be sad. It's here for you. So it's the signal primitive. When we start, introducing signal processing, it's where we start demonstrating all of these manipulations, right? So here's a signal, a pure frequency, right? What does that mean? It just has one frequency here, right? So that's this F here. We'll get into the variables, sorry. So A is the amplitude. It's how, not even going to say how loud it is, because that's not exactly right, but it's definitely one way to think about it. And then this is the period, which is tau. Then the frequency is 1 over the period. And then the phase shift is phi, I think. And that's how much the wave is shifted. So, if you shift by pi, you'd end up here. If you shift by 2 pi, you'll end up where you started, right? So obviously, like, this is cyclical for every 2 pi. So that's fundamental. And then energy is just the integral of the sine squared. And we can look at this wave also in the frequency domain, which we'll get into a little bit later as well. So this has a frequency of omega over 2 pi, and then this will have a frequency of omega here. Cool. And then we have real waves, right? So we heard a lot of real waves already today. Real waves are not just sine waves, right? Like Anthony showed on Monday, he just played a sine wave and it just sounds like a beep, right? It just sounds like one frequency interesting happening. And then he asked, how to make this sound like an instrument? And everyone said add harmonics, right? So this is actually the harmonic spectrum of a vibrating string. It does not just have one frequency, right? It might have like a more dominant frequency and more frequencies are and obviously it doesn't have every frequency, but it has one frequency, one what we call base frequency, and then it has or fundamental frequency, and then it has multiples of that fundamental frequency. So we get into a little bit more what we hear, and we already touched on this a bit on Monday. But because the way we hear sound, like Anthony mentioned on Monday, is not linear with the pressure of the sound wave. So if you increase the volume by 2, you don't hear a double amount of sound, right? So Alex Graham Bell is actually the one who discovered that you have to increase things exponentially to get a double increase of sound. So this is what we call the decibel. It's really much in line with how humans perceive sound. And so that's an important thing to know, is it's very based on what our perception of sound is. And, you know, a lot of these things are. And then as well as frequency, right? Anthony also mentioned that the inner workings of your ear, the cochlea, hear frequency logarithmically. These are all laid out logarithmically. I forget what they're called in the cochlea, but the vibrating hairs on your cochlea increase logarithmically, not linearly. So we then have the mel, which takes the log of the frequency, so we can have a more accurate understanding, and then some scaling here and there also to ensure that it's more relevant or more like what humans perceive. So this is an example of a mel spectrogram. You might have seen it before. You'll definitely see more later. The x-axis here represents time, and the y-axis represents frequency. And the color intensity is the loudness of each frequency at a given point in time. Cool. So this is just a comparison of the 3 types of spectrograms, like measures of frequency. This is amplitude with respect to time, and this is frequency with respect to time, and these are after running those frequencies through a mel spectrogram. Cool. So one of the most fundamental parts that I alluded to earlier in DSP is sampling. So let's say we have a weather station, and the weather station wants to try to recreate this, to sample this wave, right? And we have these like high points here. So we can try a few different ways of sampling it. Maybe we have a threshold and we'll just measure like those 2 points, like at those 2 points above the threshold. Maybe we'll measure the low points. But like also the up and down is kind of important, and we want to be able to, you know, reproduce it exactly, right? So we probably should just take more data points, right? But you know, we have limitations. We can't just measure indefinitely. So what do we do? Well, let's first measure it. So the analog to digital converter will take samples of the point take samples of the wave along certain points. And this, difference here is the sampling rate that you've determined. And we saw this a bit earlier. And we'll do some filtering on that signal and then reproduce the analog one if that's, or analyze it, whatever the, requirement of the system is. So like I said, that's the period and this is the rate. So the main problem here is that if we sample at too low of a rate, we might end up running into a problem called aliasing. So aliasing is a fancy word for loss of information. It essentially means that, let's say I have this wave, right? And then I sample at these points, okay? We could reproduce like more than one type of wave if we sample at these points. We can reproduce this bigger one, this one with a larger or a smaller frequency, and then this one with a bigger frequency, right? So which is the true wave? And the most important thing to remember here is that this led to the development of what we call the Nyquist rate. So the Nyquist rate states that in order to accurately reconstruct, or not even reconstruct, but resemble or have a good understanding and match the frequency of the wave you've sampled, you have to sample at least 2 times the largest present frequency. So Anthony mentioned that CDs normally sample at a rate of 44,100 hertz, and that's because normal human frequency doesn't go above 20,000 hertz, normal human speaking. So that pops up over and over. If you want to know why, I can send you resources on that. It's pretty cool, actually. It comes from the fact that the sine equation has there are 3 different unknowns in that equation, and to correctly reconstruct all of them, we need more than 3 data points per period. Anyway, that's a tangent. If you want to know more about that, I can send you some resources that are pretty cool. Cool. And now we process. Any questions so far? I've kind of been blazing. Awesome. I'm going through a lot of topics. They're pretty important, signal processing topics. So if you're interested in any of them or want more details, please reach out to me. Awesome. So now we have to talk about the frequency domain. So a lot of the times when we take samples of signals, like we saw in the, with the balloon popping, it looks just kind of like, a mess a lot of the time. And so using the frequency domain is extremely important in trying to figure out the nature and what things have occurred, what frequencies have occurred in a given time domain signal. So we have this example here. And we'll talk about the Fourier transform. So let's say I have these 3 waves and they're added together. So we can see very clearly what the frequencies are, right, in the first 3. But we've scaled them like by some C or whatever, and we've added them all together. I don't think it's very clear at this point to figure out what the frequencies are, right? And what 3 frequencies, even though it's only 3, right? What 3 frequencies have combined to form the wave here on the bottom. And so this is where the Fourier transform comes in. So, excuse me, we have this time domain signal here. Let's say it's this one, and it's a combination of these 2 waves. These 2 waves, like it's a little bit tough to see, obviously with a human eye, but especially mathematically also, like cannot see exactly where all of these waves come from. And so we take the Fourier transform of this. So like the frequencies of those produced waves. And so we can do analysis on them, and especially so we can do filtering and convolution, which we'll talk about in a bit, which is actually one of the most important parts of the Fourier transform. So this is just a side-by-side of waves or time signals in the time domain and in the frequency domain, and they have all of these different frequency outputs. We can point some out. So here's random noise, which we also can call white noise. White noise just has, you know, a line in the frequency domain, and that's because it has essentially all of the frequencies. So this is pointing out that it has all of the frequencies in the frequency domain, and they're all added together uniformly to produce random noise. The sine wave here has just an impulse here. The triangle has a decayed impulse, and those are delineated at length if you just, you know, looked up Fourier transform of triangle or whatever. But this is just to kind of give you some intuition and how useful this can be. So let's define what a complex exponential is. It's essentially a sum of a real part of a real wave and a complex one. And this will be your phasor. So I'm sure we've seen this before, right? This angle here is the phase shift. And as we go around, we, you know, will replicate this wave here. It's not exactly intuitive right now of why like if we have real waves, why they have a complex part, and I won't get into that, but if you're interested, let me know. Cool. So this is the Fourier transform. It looks quite mathematically complicated, and we're not going to get too in-depth into it. It's just important to know about, and this is obviously the continuous one. What's important to notice is that we have the time domain here, right, multiplied by this complex exponential, and we get out the signal in the frequency domain. And then the inverse right here is we do a very similar integral of the frequency signal, and we get out the time signal. This is an especially important signal in DSP. It's called the Dirac delta. So it's essentially a signal just at 0, and it goes up to 1. And so if you think about it, like you can create any signal with a Dirac delta, and you can make any signal with a Dirac delta. Like all you have to do is scale it and move it, right? Any signal in DSP. So that's extremely important and used a lot in convolution, and as we'll see shortly. So this is a sequence of impulses, and this is what I was alluding to earlier. One of the most important concepts is the sifting property of the impulse, which is when you take an impulse that's at lambda. So this is, you know, this is x minus x naught, right? So delta of x minus x naught is a delta that is centered at x naught. So if you take a delta that is centered at lambda and you multiply it by f of t, then you get f of lambda. So in that way, we can sift and move any of our signals with the Dirac delta. The Dirac delta is very useful and is like basis again for convolution, as we'll see in a second. Like I said, so this is, you know, the sampled signal, and these are all, you know, instances of impulses. So like these are all impulses at specific amplitudes and shifts, right? So let's talk about filtering, because that's an excellent application of the Dirac delta. So these are analog filters. This is not exactly the filtering that we do now. It is done now, but not non-DSP. So these are different types of filters. You know, we send, you know, a voltage in, and we get, you know, these are kind of what the filters look like. And then we get a voltage out. And we use this block diagram form to represent the filtering. So in the digital filter system, we have really the same sort of thing. We can add them together, can multiply. Excuse me. We can have a unit delay. We can, yeah. Sorry. So this is the Z transform. It's analogous to, sorry, one second. It's analogous to, it's how we do a lot of analysis of the signal in the discrete space. So these are all of the, transform pairs. And then last but not least, we'll talk about convolution a bit, which is where I was headed. Yeah, Anthony corrects me. Sorry, it's not the discrete Fourier transform, it's the discrete Laplace transform. So why I mentioned convolution why I mentioned the impulse response was important was that it characterizes a filter. So this H of n that you see here is what we call the impulse response of a filter. So if I have a low pass filter, for example, and I pass a Dirac delta through it, it'll output its impulse response, and that impulse response is how we compute the output of putting any sort of signal through that filter. So, for example, if I wanted to know what would happen if I put x of n through a filter with h of n, where h of n is the impulse response of a given filter, I compute the convolution of x of n and h of n, right? So this is the convolution. You might have heard of it. It's flip and drag, if you've heard of that. And you might have heard of like convolutional neural networks. Like this is the mathematical basis for that. So why is the convolution so important? It's important because it's how we know what the output of a given waveform is to a given filter. But it's mathematically complicated. And one of the best things of the Fourier transform is that it simplifies the convolution to multiplication. So that's right here. So where in the time domain we had y of n and h of n, y of n is h of n convoluted with x of n. In the Z transform space, we have y of z is equivalent to h of z times x of z. So that's what we call a transfer function. And again, it's extremely important in signal processing and is fundamental in how we construct our filters, how we know what's going to be the output of our filters. So this is a simple example of what one of those block diagrams might look like. And we have the FFT written here, which I mentioned was a speed up. What I mentioned, there's speed ups of the discrete Fourier transform. The FFT is the fast Fourier transform, which utilizes symmetry and linear algebra to quickly compute the discrete Fourier transform. So it's used a lot now. We don't really use the pure DFT anymore. We use the FFT. And last but not least, we have all of these. There's a lot of them are written up for you. Fourier transform properties. That's all I have for you guys today. Are there any questions? I did speed through some of it. Cool. Sorry, I didn't write a concluding slide. We finished right on time, which is awesome. So, like I said, we're going to be postponing tomorrow's lecture to Monday because of noise engineering being in LA and having to deal with everything that's going on in LA right now. So we'll be putting that at 4 p.m. and then we'll be moving the lecture on Monday to Tuesday. So that's Nico's lecture. Get excited. That's on subtractive synthesis. So next week will be a pretty heavy week, heavy and fun. So yeah, if there's any questions, email me. If you wanted any of the resources I mentioned, please let me know. And stay safe. Yes, Anthony. I don't know how to answer your question.
I just clicked the wrong button.
Oh, okay. Did you mean